Okay, so I think we've done a pretty good job on the list. And of course, since I post the MDE 60 and 61 stuff in Canvas under announcements, hopefully you know where to look for that. Same place you look for any of the other videos, okay? You can see what I've done on the same problems in those classes. If there's a problem we haven't gone over in here, you'll find it in one of those, okay? I want to talk more specifically about graphing like rational functions, polynomials, okay? What we've done here kind of covers everything for the basic functions up through quadratic functions. Remember to graph a quadratic function. Find the zeros, find the axis of symmetry, find the y-intercepts, use transformations, okay? Something we've done a number of times, and I certainly expect you to be able to do that. You can be almost sure that you're going to cover that on the test. Not 100% sure, but probably 80% sure, okay? And maybe 100% sure, I haven't set them up yet. Okay. So, how to graph a polynomial. Okay, I'm going to discuss this. I want you to take just a minute and write down what you would do to graph a polynomial, just in words. What would you do? Okay, now to graph a polynomial, you do pretty much what you do with any function. You start out by finding the intercepts, okay? Okay, well. No, it did, yeah, it did start recording. I never know. Okay, well, I'm not going to do that. We've done it 100 times. But I want to give you a focus on what you do. And most of you pretty much wrote that down, okay? Some of you drew a picture with arrows at the X and Y coordinates. Make sure you know how to plug in Y equals 0 to find the X intercepts, okay? And sometimes there aren't X intercepts. Now, if you've got a function that's defined for X equals 0, you will get Y intercepts, okay? And if it's a polynomial, you are going to get a Y-intercept. Now, an example of a basic function where you don't get a Y-intercept is 1 over X, or 1 over X squared. Okay, well, we get to that when we talk about rational functions, because those are actually power functions, but they're rational functions, okay? They're not polynomials. Polynomials, just all non-negative powers of X, and all those powers are defined for every possible value of X, including 0, okay? So if it's a polynomial, you always get this, okay? And you should understand why you always get the Y-intercept, because you plug in X equals 0, everything's got an X in it is going to give you 0. And what you got left is just that number at the end. There's your Y-intercept. Okay. You don't always get X-intercepts. Okay. It's very possible for a polynomial to stay above the X-axis and go below the X-axis. Okay. That won't happen if you have odd powers, but if you have all even powers, and they all have positive coefficients, and then you add a positive number to the end of it, you're going to get something that stays above the X-axis. Now, replay that if you want and see how that works. I'm just emphasizing that it's very possible for polynomials to stay above the X-axis. Specifically, just, a quadratic function is a simple example of a polynomial. It's very possible for that parabola to be up high enough that it doesn't cross through the x-axis, in which case your discriminant would be 0 if you use the quadratic formula and you wouldn't get any x-intercepts. Okay, if the polynomial doesn't factor into linear factors, okay, then you don't get x-intercepts. So, call it P of S, which is a polynomial. Let's say your polynomial has this factored form. Then clearly x equals 7 is an x-intercept, right? Because your y would be 0. Okay, y is P of x, y would be 0 if x equals 7. The graph would go through the point 7, 0. If x is 7, y is 0. Okay? There are no other x values that would make y equal 0. Because x squared plus 2x plus 10 doesn't have real linear factors, okay? And you could determine that by setting this equal to 0, you get a negative under your radical. Because the 10 is positive, it's too big, makes the discriminant 0. You have a square root of what? 4 minus 40. You have a square root of negative 36 in your quadratic formula, and that's not a real number, okay? So this would have only this linear factor, okay? But it would still have zeros, right? It would at least have 1 0, okay? Here's an example of a polynomial. It would have no zeros because you set this equal to 0, you get a negative discriminant. And if you set this equal to 0, you get a negative discriminant, okay? So polynomials don't have to have zeros. They do have to have y-intercepts, okay? There's more, and of course, open math told you a little more, but that's the foundational stuff, okay? And then find the long run behavior. It's hard to write infinity down this low on the board. Okay, as x goes to infinity, y goes to what? It's either going to be infinity or negative infinity, okay? And it's easy to do that. Yeah. What does y go to as x goes to negative infinity? It's going to be infinity or negative infinity. And this is all governed by your leading term. meaning your highest power term. Okay? So if your highest power term is a positive term with an even exponent, well, a power function with an even exponent has a graph that's a lot like a parabola. The higher the exponent, the flatter it gets in the middle, but it still acts like a parabola, which means either up or down. Okay? If it's up, then as x goes to infinity, it goes to infinity. And as x goes to negative infinity, it goes to infinity. Okay? If it's an even power that goes down, then as x goes to infinity, it goes to negative infinity. And as x goes to negative infinity, it goes to negative infinity. Okay? If it's just an even power, if it's an odd power, all odd power count the polynomials. Maybe I've been going too long today. Okay, all odd power polynomials act like your cubic function, your basic cubic function. Okay. Now, if it's a positive multiple of the basic cubic function, it's up like this. If it's a negative multiple, it comes down like this. You should understand all that. It's easy to understand. Okay. But it's got to go through the x-axis. So if your leading power term is odd, you will have x-intercepts. And as x goes to infinity, well, it's either going to go up or down, depending whether it's this or this. So you're going to go to either positive infinity or negative infinity. Whatever it does on this side, it's going to do the opposite on this side, because this is down when this is, just down on this side when this is up. And this is up on this side when this is down. Now, if you understand the graphs of the basic functions, you understand what I just said. If not, you probably want to take another look as you review, okay? But that's how you determine the long-term behavior, long-run behavior of a polynomial function. There's more to it. If you understand these basics, you have a good foundation. And then if you did the problems and thought through them and learned what open math tells you and some of the other stuff we talked about in class, you'll be able to do it. But I'm not going to confuse you with it right now. Okay? And there's stuff we didn't cover. We didn't really, well, we didn't talk about all the tricks you can use to factor, because they almost never work in applications anyway. It's a choice I made. There are good reasons why you would. If I was trying to train mathematicians, I'd definitely do it. Okay? And if you become a mathematician, you come back and shake your finger at me, tell me, I wish you'd have done that. But if you have the ability to become a mathematician, those tricks are easy. Okay? So we skip. If you're going to become an engineer, again, you're going to find those tricks easy. You can pick them up when you need them. Okay? Focusing on the vast majority of people in a pre-calculus class, we want to be able to apply the stuff to real world. And those things don't make a hill of beans of difference. And if somebody wants to disagree with me, I could give the opposite argument. Okay, I respect it. That's my decision. Okay, so there's some sections we skipped, some things we didn't do. I would have loved to do them, but I don't want to overwhelm you any more than I've already done. Okay, now, graph the polynomial. That's kind of the basics, okay? That'll take you a long ways. If you do that much, you're going to be okay. Graph a rational function, we've got a polynomial over a polynomial. Okay. A polynomial over a polynomial What do you do? Go ahead and write it out for me. Okay, so everybody's telling me all this, which is true. You do all of it, okay? Find the intersection zeros. Okay. And I'll note that letters to use. R of x equals P of x over Q of x. If P of x makes it 0, then you got 0 over this, which is going to give you 0, right? Except if Q of x also equals 0. Unless maybe some of the zeros of P of x are also zeros. Of Q of x. Okay. Now, for most of the problems I'll give you, that's not going to be the case because I'm keeping it simpler than we really ought to. Because again, you almost never in applications run into applications where that occurs. But if a linear factor of Q of x matches a linear factor of P of x, then you can divide them out. Okay? If they have the same degree. So I'm not going to get into that. That's something you want to be careful of. So you want to maybe think about that statement and go back and review. But make sure you got the overall picture first. If you got the whole picture, except that, you're still going to do okay. Probably wouldn't be what I'd call A work, but it would be passing work at least. Okay. So you look for the zeros of P of x. Then if Q of x has zeros that match zeros of P of x, you do what you do. And I'm going to leave that to you because I don't want to confuse the issue. Okay. That's something you will have seen in your homework. So you might want to review it. If you've got everything else down. Okay. And of course, the y-intercept occurs when x equals 0. Unless Q of x equals 0 when x equals 0, you're going to get y-intercepts. Okay. If Q of 0 equals 0, the function is undefined when x equals 0 because division by 0 is undefined. Okay. And if Q of x equals 0, Q of 0 equals 0, then you either have a vertical asymptote when x equals 0, or you just have an undefined point when x equals 0. Okay. Again, the second case doesn't occur much in the real world. And if it does, you can deal with it then. Okay. You can have your toolkit, you can review, you can look up what happens. Now, it doesn't mean that that won't occur in the exam, but again, it's not something that you can totally dismiss. But it's something, if you don't know, it's not going to be that heavily comfort on the exam that it'll kill your grade. Unless you're trying to make a high A, okay? Something that might not even occur. And if it does, it won't be worth that many points. Maybe enough to knock you out of an A, but not enough to knock you out of a passing grade. Decent grade. So review it if you're in good shape and have time. Or your goal is to ace the course. Sorry, about to say something else. It's getting late, I guess. Anyhow, you go on. You find asymptotes. Can't read that last. Can't read the second half of that word, but the way it starts, you can tell who says asymptotes. Okay. Unless maybe those zeros match zeros of P of X, then you got to look at the degrees of the zeros and all that stuff. Okay. And then long run behavior. Okay. As X goes infinity, as X goes negative infinity. And I don't have room to write that out, but review it, okay? It goes as a leading term of the numerator, leading term of the denominator, also the degree of the numerator and the degree of the denominator. If the degree of the numerator is greater than the degree of the denominator, okay, then you're going to tend to approach infinity or negative infinity. If the degree of the denominator is greater than the degree of the numerator, you're going to tend to approach zero. Yeah, both ends. If the degrees are equal, then you're going to tend to approach a constant value of y, but not zero. And if the degree of the numerator is 1 greater than the degree of the denominator, you're going to have a slant asymptote that can be determined by long division. Okay? You want to review all those things. And I'll come back to them if I have time after we talked about everything else. Okay? But there's the beginning, and the rest is something you have a bunch of problems on. Okay, there are rules, and they aren't that difficult to understand, so you're going to want to review. These are the most fundamental essence of rational functions and polynomials. Okay. I said all this profound stuff and didn't record it. I did that last class, didn't I? I mean, like an hour ago, plus last time. Getting too late in the semester. We've got all of about 39 minutes left in the semester. Okay, well, here. We talked about the graph of b to the x, just to summarize. Picture that was prominently displayed in your text. Look like this. If b is bigger than 1, you get this. If b is less than 1, you get this. Okay. You know, b equals 1, of course, you just get a flat line. And the reasons are really obvious if you just do it with a few numbers. 2 to the x graph looks like this, doesn't it? Okay. Well, the 1/2 to the x graph would look like this. If 1 is here, and of course you can put 1 anywhere, but if 1 happens to be here, then for the white graph, here's your value of B. Because of course, B to the 1 equals B, and the value of Y on this graph when X equals 1 should be B to the 1, and that's B. Okay. For the decreasing graph, which I've kind of blew up here, turned it blue, your B value is going to be down here. It's going to be less than 1. Okay. Now, Y equals 1 plus R to the T. Example of that is interest rate R compounded every year. We developed that in detail, 10% interest on $1,000. You want to understand that. If B is bigger than 1, you have a graph that can model compound interest for the right value of B. Okay. If B is less than 1, well, you can model radioactive decay. Or as I said, you could model, okay, if you have a certain amount of money and inflation's running at a certain rate, then R would be a negative number, which would make this less than 1. So it'd be like your B is less than 1, the value of your money starts going down, okay? Now, hopefully, if you're in an inflationary period, which we are right now, your pay goes up as fast as your money goes down, and you don't lose any buying power. Maybe your pay goes up faster than inflation goes down, which isn't tending to happen right now, but there's some indication it might. Okay, well, the whole thing about inflation is very complex. So we're not going to try to analyze it. Just that's the way things work, and it's all exponential. The effect is exponential. The overall effect. Okay. Effect of interest rates, the effect of inflation. Okay. Interest tends to take you up, inflation tends to take you down. Hopefully they at least balance. So I guess I want to pose a question. You have a word for R? You have a word for 1 plus R. How does this relate to this? Okay, so if you write a couple of little phrases down, that's okay. If you can't write anything down, I'll say more, okay? Okay, this time I'm actually recording. Didn't see too much. A couple of connections. How's this related to this? Well, first of all, B and 1 plus R are the same thing. They're the base of your exponential function, right? Okay. But it's a different form. If R is greater than 0, then since B and 1 plus R are the same thing, if R is greater than 0, 1 plus R is greater than 1, right? In other words, R is any positive number. That makes B positive, gives you an upward graph, okay? If R is negative, which would be in a deflationary period or, that's not what I wanted to say. If your interest rates go negative, okay, then you borrow money and have to pay back less than what you borrow. But that's because your money buys less, okay? That can actually happen, although it's generally considered to be a really bad thing for reasons I don't totally understand because I'm not an economist. Don't know that much about economy. Okay, so R is bigger than 0, B is bigger than 1. If R is less than 0, B is less than 1. R could be less than 0 for radioactive decay. The activity of your sample goes down by 10% every time period, okay? As opposed to that going up by 10%. So those are important things. Those are really fundamental things about exponential functions. There's another way of writing it, which is e to the kt. And I'll just make a statement that that's just e to the k raised to the t. That's b to the t where b equals e to the k. So for example, if you wanted to write b to the x in this form, if you know what k is, well, then you know what b would be, right? But if you know what b is, how would you find k? Well, you convert this to logarithmic form. That's how you solve exponential equations, okay? Then you get k equals log base b of e, okay? Sorry, log base e of b. And that's what you call the natural log of natural log of b. Okay, well, that kind of brings us around to what you do with exponential equations. You got this rule that's given with different letters, depending what you want, but it has the same form. It says that and I might write down the form with, different, I can mix up the A and the C, it doesn't really matter. The power of B equal to something else is equivalent to the log to the base B, B being the base of your exponential. It's going to also be the base of your logarithm, okay? And then, now there are good reasons for this, but you don't want A and C to be in the same place, whether that makes any sense or not. But that becomes log base B of C equals A. So that if you have an equation like this, where let's say you're trying to solve for X and X is up here in the exponent, you can't do anything with it, but if you change it to this form, your A contains your X, and now you just have an equation that hopefully you can do something with. Now we've done a lot with that. Spent a lot of time reversing one equation to another, and then your assignment had many, many examples of that, where you probably got in there and just started mechanically doing it without thinking about it. That's inevitable. You do too many problems, but you got to get used to the idea, okay? But it's pretty easy to solve the equations you're going to run into, okay? So just using this, it's clear that this is equivalent to this. Now you might have to think about that. We've been over it a number of times. We don't have a whole lot of time to talk about it, but it's something that you did pretty well with when it was assigned. So just know to review it, because you're going to see equations that you have to solve, okay? Now, Okay, want to find an exponential function that passes through these points. Now, when I say these are your basic exponential functions, okay, you can always multiply them by a number and still have an exponential function. Depending on your author, you can do vertical shift and still have an exponential function, okay? And that's the key to the application problems. And one of the most important application problems is if you know 2 points on a graph, which means if you have information that tells you the value of X or the value of Y for one value of X and the value of Y for another value of X, then you can get 2 points on the graph, and then that gives you a representation of the information you have, and you can write them 2 equations. The easiest representation, and I can write my constant in there, is the b to the x. Okay, then you get y1 equals ab to the x. Well, in other words, whatever these 2 numbers are, the first one goes in for x, the second one goes in for y, and you get an equation. Okay. Now, if you want examples, go back and look at my videos, look at the videos that Open Math gives you, look at videos anywhere, okay? Look under fit 2 points to an exponential function, okay? If you have the information, you get these 2 equations. And you can solve the first one for A. Plug that into the second equation, you get y2 equals y1 over b to the x1 times b to the x2. Now that you plug this into this equation, it's going to give you this equation. And this equals y1 times b to the x2 over b to the x1 and b to the x2 over b to the x1 is b to the x2 minus x1. Okay? Now we know x1, y1, x2, and y2. So we know that y2 equals y1 b to the x2 minus x1. We know x2 and x1, so we know the power of b. We know y1 and y2, so we can solve this for b. That's the scheme. I think it was last week. If it wasn't last week, it was late the week before where we did this, okay? And if you've got numbers, it looks a little simpler. So for example, you might get 12 equals 5b to the 7th, okay? And you solve that for b. Now, I'm not going to take the time to solve that in general, but you want to review that. Okay, that's something that's very likely to happen. I mean, you would have numbers, you wouldn't have symbols, x1, y1, x2, y2. You would have numbers, so this would all come out in numbers. So an example of this might be 7 equals 3b to the negative 4th. Okay, how would you solve that for b? Well, you divide both sides by 3, you get b to the negative 4th equals 7/3. Very simple, right? And how do you solve that? You take the negative 1/4 power b to the negative 4, because your powers multiply, and you get 1. So this is just b to the 1, or b. So this comes out b to the 1. This is just something you plug into your calculator. You're not going to calculate that in your head. You might estimate it if you got a good graph of the negative 1/4 power, but not going to make you do that. Okay. So at this stage, you just plug in your calculator and you got it. Now, if you use the form y equals ae to the kx, you can still solve it. Okay. You get immediately, you just plug your x1 and y1 into this form, you get this. You plug in your x2, y2, you get this. Then you get y1, well, a equals what you get when you divide both sides by e to the kx1, just this. So y2 would be a, which is y1 over e to the kx1 times e to the kx2, which is y2 equals y1 e to the kx1 minus it's kx2 minus kx1 equals y1 e to the k times x2 minus x1. Now, these are all numbers. You just solve for k. Now, in order to solve for k, you notice that k is in the exponent. So you better change this to logarithmic form. So you ought to be able to do that. This is actually easier. So you should definitely be able to do that. Okay. If you had a problem where I asked you to use this form, I would hope you'd be able to do that. At the A level, you'd certainly want to be able to do that. Okay. At level of, still respectable, but lower than A grades, I'd expect at least see you plug the numbers in. They give me the two simultaneous equations, solve for A, and then at some point get confused. Okay. If you do that much, then you have a reasonable foundation for going on to a good calculus course. Okay. So I realized that The board too far over here. So maybe we didn't get to see all of that, and that'd be a tragedy. I don't know why I do that. Okay, so maybe I didn't point this out, but you do this solution, you get this. And then you have y2 equals y1 times this. You saw that much. Okay. So you got to solve y2 equals this. There it is. You know, et cetera. Then an example of that would be 7 equals 3b to the negative 4, because y2 and y1 are just numbers that you're given. x2 and x1 are just numbers that you're given. So if x2 minus x1 is negative 4, y2 is 7, and y1 is 3, you would get this. So it's a little easier to look at with numbers. And if you got numbers in here, it's easy to understand how you get the solution. So what you do is you solve for b to the negative 4th, divide both sides by 3, you get b to the negative 4th equals 7/3. Then you take the negative 1/4 power of both sides. And this is something you just plug into your calculator. This side, you took the negative 1/4 power, because if you take a power of a power, you multiply the powers. And negative 4 times negative 1/4 is, as you might expect, 1. Okay? So you get b to the 1 equals this. Well, that's just b. Now that you know b, you plug that back into either of these equations, which will have numbers in them, or just into this. If you know b and x1 and y1, you got a. Okay? Then you have your model. If it's exponential form, you do a very similar thing. The steps are very similar until you get down to this point where y2 equals y1 e to the k x2 minus x1. Much like this form, except that you got that e to the k thing in there, and you got to solve for k, because that's the only thing you don't know. To solve for k, change it to the logarithmic form using this thing, which ought to be very familiar to you, especially the day you go in and take the test. Okay, make sure you're straight on that. You're going to need it. Okay, so sorry for running that off the screen and taking up extra time. Now here's an exponential model. Exponential models are extremely important. They apply to personal finance. They apply to the economy as a whole. They apply to how you analyze whatever situation you're in financially or economically or many other ways. Okay, so let's say you want to invest $2,000, end up with $5,000 15 years later. Okay. Well, then that's going to be of the form y equals a times 1 plus r to the t, where y is the value and t is your time. Okay. Or ab to the t, because you can do ab to the t, then you can figure out what r has to be, because b is 1 plus r, right? So I'd recommend you go to this form, solve it, and then realize that b and 1 plus r are just your base, just two different ways of writing your base, so you can easily figure out r. Okay? If we put this information on a graph, this tells you 2 points on the graph. I want to see if you can quickly jot down a graph and show me the 2 points that you know have to be on that graph. Okay, well, if we want to put 2 points on the graph, well, y is going to be $5,000 and t is 15 years, right? Now, that should be a no-brainer if you've done the application problems. Most of you have done, but you might want to go back and look at the application problems because there will be one. Whether it'll be population, radioactive decay, money, okay? Going to be probably one of those things or something closely related. So anyhow, when t is 15, the point really bad looking 5, but there it is. Okay. Point on the graph. So when I said over here, you get 2 points in a graph. Okay. When you did the application section, go back and look at what you did and see how it matches this model. See how every problem in the application section told you something about a graph of an exponential function, because that's the visual key to being able to interpret the data. Once you've got the 2 points in the form of an exponential function, everything else comes out pretty easily if you do the algebra. Okay? And I think you can do the algebra. You just got to remember the laws of exponents and how to change an exponential to a logarithmic if necessary. Okay? So we have that. Now, what's the other point? What's the t-coordinate of the other point on your graph? Can you show me with your fingers? Got one. So. Okay. Okay, now, votes I'm saying are for 2, right? Now, 2 does have something to do with it, and nobody has 2,000 fingers. So it's really an unreasonable question if 2,000 was the answer, right? So you could have concluded that either I expected you to understand that this should be in thousands, or they don't have enough fingers, so that's not the answer. Okay, well, that joking aside. Well, I said, what's the t-coordinate, didn't I? What's t stand for? Time. $2,000 a time? $2,000 is a value, right? Okay, so what's the time? Yes. Okay. Now you got to be straight on that. You really have to understand the connection between the words and the graph. Okay. So, and 2,000 is your value. Well, clearly then you got 2,000 here. Okay. Make sense? All right. That means that you have n equals 0. So you have this point. This is the point 0, 2,000. So you got to be careful that you know which variable is which. Very easy to switch them. I do it all the time. Okay. I don't think you picked it up from me because I don't think I've done it that much in this class. I'm thinking through something and I'm tired. Okay. I might reverse it. And most people will give me an opportunity. I shouldn't, after a lot of experience, but I know I do. Okay. So, make sure that's visible. Well, now it becomes pretty easy. Okay. We'll use AB to the T. Yeah, y is 15. No, it isn't. Is y 15? What's 15? See what I mean by reversing? I certainly know the difference, but when I look quickly, I just got to watch myself. I realized that was going to make sense, but okay. Y is 5,000 and T is 15, right? Exactly what I wrote. When T is 15, Y is 5,000. So if I'm looking at what I wrote, I can tell what goes where, and I can check and make sure it makes sense. Okay. So M, when T is 0, Y is 2,000, right? So okay. Now the shortest way to solve this is to realize b to the 0 is 1. So you already know that a is 2,000. Then all you got to do is solve for b, right? I'm going to pretend I don't know that. I'm going to solve this for a, and then plug in. Okay. See if I get the same thing. And this is not the best choice, but it works. You can't really go wrong as long as you stay within the rules of algebra. Okay, so we get A is 5,000 over b to the 15th. We plug that into the second equation and we get 2,000 over b to the 15th times b to the 0. Give myself more room. I'll bring this up here. This says two thousands, 5,000 b to the 0 over b to the 15th. Which is 5,000 b to the 0 minus 15. So the 2,000 b to the negative 15th. Again, it would have been easier if I'd have solved this one for a, because it'd be really simple, because b to the 0 is 1. Pretending I didn't notice that. Okay, so the b to the negative 15th, we divide both sides by 5,000, it's 2,000 over 5,000. You get 2,000 over 5,000 to the negative 1/15th power. Okay. Now 2,000 over 5,000 is the same as 2 over 5, but either way, you see that this is going to give you b, because b to the negative 15 to the negative 1/15th is b to the 1, which is just b. And you take 2/5 to the negative 1/15th power. Okay. Well, then you plug this in for a and go forward. But again, we've done examples. Okay. And the key here is just once you have the information, throw it on a graph and turn this crank. Okay. Okay.